Hello. Hello. I'm Ezra. This is AP Calculus AB BC review. We're back, and today we're doing Unit 3 Advanced Differentiation. In this unit, we cover higher order derivatives, implicit differentiation, which is differentiation with variables x and y, inverse derivatives of inverse functions, and then inverse trigonometric derivatives. So let's begin. So, for higher order derivatives, basically, that is just second, third, fourth, any derivative that's more than once. So, if you take the function, for instance, something big like 3x cubed minus 9x squared plus 2x. Taking the first derivative of this, it's just going to be 9x squared minus 18x plus 2. This is a standard power rule derivative. However, we can then take this multiple times. So we call this the second derivative. So this is a higher order derivative, which all you're doing is just taking the derivative function and then taking the derivative again. So we'll have 18x minus 18. And then you can keep going. F triple prime of x is our third derivative, which here is just going to be 18. Now, this works again. You can do this for pretty much anything. If you have even 2x squared minus 1 over x, you can take the first derivative, which is going to be 4x plus 1 over x squared. Because this negative 1 over x is essentially negative x to the negative 1. So you move the negative 1 down, it becomes positive x, subtract 1, x to the negative 2, which is this. Okay, now let's take it again. The double derivative, second derivative, whatever you want to call it, 4 minus, because if we have x to the negative 2, we bring the negative 2 over, subtract 1. So we have minus 2 over x to the 3. And then we can keep taking this derivative because although normal polynomial functions like x cubed will eventually turn into nothing, 3x squared, 6x, 6, and then 0, rational functions will go on forever, and we can see that. Take the third derivative. It's going to be positive 6 over x to the fourth. Fourth derivative, negative 24 over x to the fifth. This will keep going. This is never going to go away. So that is essentially how to find higher order derivatives. And specifically, the second derivative is used a lot in future units, as well as the first derivative, of course. So our next topic is implicit differentiation. So what this is essentially saying is if you have some sort of function, let's take a simple circle right here, right? If you wanted to take the derivative with respect to x, how would you do that? Well, derivative of x squared with respect to x is just 2x. However, the derivative of y with respect to x is a little bit different. If you were to take dy over dx of some sort of y function, right? That doesn't really make any sense. So what we have to think about here is the chain rule. So this y squared function is essentially y on the inside as its own function inside of x squared. So if you were to take the derivative of y inside of x squared, you would have 2y, right? Because y inside of x squared, you bring the 2 down, minus 1 equals 2y times the derivative of y, which is dy over dx, or you can write it as 2y times y prime. That's what implicit differentiation really is. When you take the derivative of y, it's like this y is inside of an x function, so you need every single y term that you take the derivative of has to be multiplied by a dy over dx. So in this case, you would have something like this, and then isolate for dy dx, which I will show you in a second. So let's give a function x cubed minus 2xy plus y equals 2. All right? X cubed just becomes 3x squared. Minus 2xy, we have to use product rule. So for the first part, derivative of the first times the second, derivative of x is 1, and the y stays the same. So it's minus 2y. Now we have keep the first, derivative of the second. Derivative of y is 1 times your dy over dx because we're using the chain rule. So now it's going to be minus 2x dy over dx plus, again, derivative of y is just 1 dy over dx. And then derivative of a constant is 0. So now we have this long equation. But what we can do is isolate for the dy over dx. So this term has a dy over dx, and then this term is a dy over dx. So we can move these both onto this side. So now we will have 3x squared minus 2y equals 2x dy over dx plus, or I should say minus, dy over dx. Now, if you wanted to solve for just dy over dx, you would look over here and you can factor out dy over dx because we have all of the dy over dx terms on this side. So you have 3x squared minus 2y equals dy over dx times 2x minus 1 because there's this invisible 1 right here. And now you just divide this from both sides to bring it over, and then you have your final answer as dy over dx equals 3x squared minus 2y over 2x minus 1. So if you wanted to find the derivative at this point, this is a curve, and if you wanted to find the slope at any given curve, or at any given point on the curve with respect to x, you would use this. So you need to know the x and the y of the coordinate of the point on the slope if you wanted to find out what the slope was at that point. So if I said find it at point 2, 1, just plug your 2 in for x, plug your 1 in for y, and there you go. You will have your slope at 2, 1. Now, we'll do this again with, let's take the function 3x squared or I'll just do x squared minus 2, or I'll do 3xy plus ln of y equals 1. So, let's do the same process as we did before. Now we have an ln, though, but it's just going to be the same process. Derivative of the first times the second, derivative of the second times the first, and then ln of y is going to be 1 over y, because that's the derivative, times dy over dx, which equals to 0, because this one goes away. Now, we have 2x minus 3y equals 3x dy over dx minus 1 over y dy over dx. Factor this out, so we'll have dy over dx times 3x minus 1 over y, and then you just move it over. 2x minus 3y equal, or over 3x minus 1 over y. This is your answer. Now, you can go one step further. You can take the second derivative of this. So what do we have? D squared y over dx squared. This is the notation for the second derivative. Is, now we're going to have to quotient rule. And this is going to be a long answer. So, low derivative of the high is going to be 2 minus 3 dy dx. Minus high derivative of the low, which is going to be 3 plus 1 over y squared over 3x minus 1 over y squared. Now, we have this result. This is not complete, however, because we have a dy dx over here. Oh, and something I forgot, a dy dx over here. So, what do? Well, we know dy over dx equals 2x minus 3y over 3x minus 1 over y. So, all you have to do is just plug this into here, plug this into here. And then now, this is going to be our long answer, which I'm going to try to make small. 3x minus 1 over y. 2 minus 3, 2x minus 3y over 3x minus 1 over y minus 2x minus 3y. 3 plus 1 over y squared, 2x minus 3y over 3x minus 1 over y over 3x minus 1 over y squared. That is our final answer, and it is quite long. But this is just to show you that you can have your single derivatives, which is going to just be every time you take the derivative of y, you plug on a dy over dx, and then when you take the second derivative, you will have dy dx's in your solution, which you need to substitute with the equation you already found. Okay. Next, we have not inverse trigonometric, just inverse functions in general. So, let's say we have f of x equals x cubed. You can have your inverse function, we're going to write this as y. Y equals x cubed. So when you have an inverse function, you're just swapping the x and the y. So if you want to find the derivative of this inverse function, you will have x equals y cubed, or y equals the cube root of x. And then if you wanted to find the derivative at any point, you would then take the derivative of this. So y prime equals 1/3 x to the negative 2/3, or 1/3 cube root of x squared. This would be your y prime function. However, there is a formula for this. If you have f prime -1 of x, so the derivative of the inverse of x is going to be 1 over the derivative of the inverse of x, the reciprocal, essentially. So if you took f of x equals 2, right? 2 cubed equals 8. So that means the inverse of 2 would equal to 8. So if I wanted to find the derivative at x equals 2, I would plug my 2 into here, and then that would give me 1 over f prime of 8, because the inverse of 2 is 8, as we just saw over here. Now, f prime of 8, we have to take the derivative of this, which is just 3x squared, and then 1 over f prime of 8 is 1 over 3 times 64, so 192, and that would be your answer. This can get much more complicated though, and I'm going to show you how to do it with a more complicated function. So let's take sine of x plus 2x plus 1. So if I told you find the inverse derivative at 1, let's try it. 1 over f prime f of -1 of 1. Okay. So 1, what is the inverse of 1? So we have 1 equals sine of x plus 2x plus 1. We have the 1 over here. So what is the x value going to be for these ones? Well, sine of 0 is 0. 2 times 0 is 0. So x is going to be 0. Okay. So you then have 1 of f prime of 0. 1 over f prime of 0. So take the derivative. Y prime equals cosine x plus 2. Okay. F prime of 0 is cosine of 0 plus 2. Cosine of 0 is 1. This just gives you 1/3. However, while this is correct, there is another way to do it. If you ever forget this formula, if you want to find the inverse derivative of any function, you switch the x and the y, as we know. Okay, and then we can do what we did before, implicit differentiation. Plus 2 dy over dx. dy over dx times cosine y plus 2 is equals to 1. So then dy over dx equals 1 over cosine y plus 2. Okay. Still need to know what y is, but like we said before, when you plug the 1 into your x, y will be equal to 0. That is the solution to that. So then you get 1 over cosine 0 plus 2. And that is essentially what we figured out before. So you should remember the formula of an inverse function's derivative. But if you forget, you can implicitly differentiate it. That's another way around it. Finally, and briefly, we're going to talk about inverse trig derivatives. And this is very simple. These are formulas you will just need to memorize. And the three that are relevant and that we will talk about, well, really it's two, but it's these two, is the arc trigs of the main three trig functions. So, these you will just have to memorize. Derivative of arc sine is 1 over square root of 1 minus x squared. Arc cosine is the same thing, but negative. So negative 1 over 1 minus x squared. And then arctan is 1 over 1 plus x squared. So the reason you only really need to memorize these two is because arc cosine is just negative of arc sine. So you can just think about that and then don't even worry about arc cosine. So this also works with the chain rule. If you have arctan of x squared, this will be 1 over 1 plus x squared squared times the derivative of x squared. So then you get 2x over 1 plus x to the fourth. So those formulas, no getting around it. You do need to memorize them. And either arcsine or arctangent, one of the two will appear on the test at least once. So, key takeaways. If you want to take the derivative multiple times, called a higher order derivative, you just take it multiple times. You just take the x squared, or x cubed, 3x squared, 6x, dot, dot, dot. Implicit differentiation. There will always be one implicit differentiation question on the test. And for the higher order derivatives, there will be multiple mentions of it on the test. Multiple. So you need to know that. And then inverse derivatives do not always appear, but they can. And then derivatives of arcsine and arctangent. These are what you should be taking away. Thanks for watching.